Okay, so we're going in reverse. We got a scenario here, and the scenario is, again, this is the opposite of the lab. So in this case, I have to give you information that you didn't have in the lab. And if you can see how this is like the lab and how it's not like the lab, going backwards and forward, you see everything. So here's the conditions I have to give you. Very important. I have to give you the concentration of the, I have to give you the concentration of the acid. This is not working out, okay, as I expected. So so this has to be given to you, all right, the concentration of this acid, all right? That is utmost, all right? That's what we were finding in the lab, okay? So the reason is you can't find it given a blank slate, so I'm giving you the concentration, all right? I'm giving you the Ka. Of course I have to, because how did we get the Ka? We had to have a graph to get the pKa, right? So all these things I have to give you that are just different, but still connected. All right, so there's 5 points we need here, all right? So I'm going to go after the most important point. For me, the most important point is the equivalence point, okay? And why is that? Because I can start building my graph, and everything's going to follow my equivalence point. I know the concentration of the acid that's in my beaker. I know how much in the beaker I have. Okay, so I think molarity, and I think liters, I think, this is going to give me the moles of what's in the beaker. And I know, okay, that I have to deliver enough moles of base to equal the hydroxides with my weak acid. So if it does help you, draw yourself the conditions. And you probably don't have to as we go through this. So what I'm going to do is just, just as an aside, as I keep doing, here is my burette. It's like a splinter, but hey, that's all I got. And I've got my NaOH in here. We're dropping a base. Now, I've been showing you these, the base being standardized and the acid underneath. Yes? I don't know if I posted it yet because I've been all AP Chem. The homework is going to be in class. I'm going to continue on with action potentials, and then you're going to resubmit your homework again tonight. So that's pretty much the homework, okay? So NaOH is going to be 0.04 molar, and of course, it's really important to understand that we have our weak acid in here, and that, of course, the weak acid is 0.10. I'm just going to write HA to make things easy, and then that's molarity, and of course, I have 24 milliliters. So clearly, I keep adding base until I stop, okay, or until I reach equivalence. So I want to find my equivalence point. So I'm starting with number 4. At least for me, it's important to get that graphically, because where do I go from there if I don't know what my equivalence volume is? So I'm starting with number 4, at least part of it. So what do I know? I know that I have 24 milliliters, which works out to be 0.024 liters of acid, and I know that I have 0.1 molar, making life easy for myself with these 0.1 molars, okay? And I should know molarity times liters gives me moles, and 0.1 times 0.04 gives me 0.0024 moles of H plus that are in my what? Beaker. Okay, that's right in here. Guess what? At equivalence, if you haven't figured this out, that must mean that we have what? 0.0024 moles of hydroxide. Don't know that, I don't know where you've been. Okay? Now, question is, when we had a graph, we could find the asymptote and find exactly where that position is. We got to find that volume. So how much volume of base do I add to make 0.004? Well, it's very simple. Molarity is equal to moles over liter. Well, what do I know? I know the concentration is 0.04 molar. I know the moles has to be equal to the moles in the what? Beaker. So that's 0.0024 moles. And now I'm going to solve for my liter. Okay? So when I solve and do the math, it winds up being rearranged 0.0024 divide by 0.04, and I get 0.06. 0.06. That's liters, okay, which we should know is 60 milliliters. I just gave myself an important point to start. And now, although I don't know what the pH is, we'll get there, I do have some important piece of information. I know that at 60 milliliters, or 0.06, there's where my asymptote lies. Or there's where at least my X value of the point for equivalence. Now, once I have that, boy, I can get the ball rolling. If I know 60 milliliters delivers enough hydroxides to completely neutralize the H+, then half equivalence point has to be where? 30. So simple. So now I have another volume. Can't put a point there yet, but I'm going to go there. And since I got to this position, it makes sense to me. Let's go finish point 2. I need to know what the pH is. But they gave me an important clue. And what's that? Ka. In the lab, you took that point and found the pH. But now we're going to take the Ka and convert that to a pH. And because of the Hender-Hasselbalch, and I'm not going to beat this to a brown pulp, I think I have. So working on point, number 2 here, probably the easiest now, once I know that the volume is 30, what's the pH? Well, what we know very simply is that the pH equals the pKa for the acid at the half equivalence point. I don't think I need to explain why anymore. Okay, so what do we have? We have the Ka. This is where people are making some simple errors, but that's good. Get them out of the way. 6.3 times 10 negative 5 is my Ka. So my Ka is 6.3 times 10 to the negative 5. Little p, party people, means negative log. Convert it to an exponent. So take the negative log of this, and that's going to be your pKa, which is going to be the pH, at that point. So I take my 6.3, and I go to the negative 5, and I take the negative log of that, or I probably should have done that first, but I'm told. Error, because my fingers are big. So negative log at some point, 6.3, second function. If you're in that caret key and you do it this way, boy, it can be havoc. Need a second function here to the negative 5. Close my parentheses. I think I did this right. Okay, so I get a pKa, which is the pH, which is the negative log of the Ka at half equivalence, to be 4.2. And that is going to finish out that point number 2. But I needed the equivalence volume to start that. So now at 4.2, at 30, booyah, I got point number 2. Okay? I'm going to be crazy and go in order. You could jump around, jump around if you want. But I'm going to go after point 1. Okay? Because point 1, I have all the information. Point 1 is what is the initial pH? Now, what's really important, as I've been saying before, let's just kind of quickly review. There are 3 reactions here. Okay? We have our acid and water. Okay? So let's do that. H7,502. Now, we have H7, that's C7, H5, O2. Okay, and this is sitting in water because I'm looking for the what? Initial pH. This is equilibrium. Okay? And so this is going to give a few H's, or at least it's going to give that H plus to water. It's going to make the H3O plus, and of course a conjugate base. Will it make a lot? No, because it's a weak acid. How do I know? The Ka is pretty small. But it's going to go forward somewhat. Okay, the question is what? All right, so this is point 1's reaction. This is just it's sitting in water. You've got to recognize this is not the titration. Okay? This is the initial pH. And guess what? We want to solve for that. Now, if you want to do, I don't think we have to, okay, what do we know? The Ka is equal to what? This x squared over the concentration of what? I gave you the concentration. See, we can go right to it. It's 0.1 We know the Ka. Okay, 6.3 times 10 negative 5. Anybody lost how I'm doing this? Okay, I'm doing an equilibrium problem, essentially, right? Products of reactants, so this is x squared. Notice this is a liquid, so it doesn't apply. In truth, isn't this really a minus x? But it's insignificant, so small compared to 0.1. So we're going to times 0.1 times 6.3 times, so it's going to get smaller, but you should be able to do this math, guys. Okay, this is something where you could see this. You could see this in a multiple choice question with this math. 0.1 times something that has an exponent to negative 5 is going to get smaller, okay? Going to get smaller by 1/10. So when I times this together, this becomes 6.3 times 10 to the negative 6. Okay, you should be able to handle that without a calculator. Those are the kind of things you'll see in the multiple choice. Now, I get it if you can't square root 6.3. I get that. Okay, so we need to do what? That's equal to my x squared, and of course I square root both sides. How many times have we done this, guys? It's coming over and over and over again. And this is the classic what? Formula for acid-base equilibrium problems, because what? One acid gives off one H for one conjugate base always. Even if it's a diprotic acid, we always deal with the acids individual. Learn about that in the next step. So, square root of that. Don't fall in love with always that, like in KSPs. And some people think like yesterday, well, KSPs, KSP, KEQ, KA, KB are all the same thing, just talking about different reactions at equilibrium. Yes? Okay, so square root. Square root 6.3, second function here, to the negative 6. Okay, what I get for my x, okay, is equal to 0.0025, we'll say. And what did I solve for? Hello. I solve for my hydronium ion concentration, which is synonymous for H+. And what am I looking for? Initial pH. So I'm going to negative log this guy. Okay, so negative log.
Wait, is that the concentration of the moles?
Ah, great question. Great question. Okay, if we're in equilibrium, and you've got to know when you are. If you're in equilibrium, we did a derivation a long time ago that the entropy of reactions, which lead us to say who is spontaneous and who works, is all tied to concentrations of aqueous solutions or partial pressures of gases. Why? Because a gas gets diluted, entropy is increasing. A concentration dilutes. So anytime I'm dealing with equilibrium, it's a great question. People get it wrong. I must be in molarity. It's about concentrations because K, KQ, KSP, whatever, is the products over reactants. Coefficients become exponents, and solids and liquids do not apply. Why don't solids and liquids do not apply? Because they don't have a concentration. They don't have a molarity. I should be doing this in brackets. I'm sorry for going fast, but brackets mean concentration. Equilibrium is a value that tells us what? I mean, everything's connected. Who's winning, the forward or the reverse? Who is more spontaneous? Well, in this case, that the Ka is what? So small, who is more spontaneous? The reverse reaction. So spontaneity is tied to all of this, but we can only measure spontaneity with concentrations of ions. By the way, that's negative, sorry. Okay? Or concentrations of things that dissolve, but not things that are liquids or solid. Great question. Because, hey, when do I use moles? When I'm doing a stoichiometry table, the driven reaction. Great question. Okay, so negative log of that sucker. It might bite its candy, so I'm not sure if it's a sucker, but 2.6. And booyah, I'm done with that point. So 2.6 is my pH, and let's do that. You've got to know what kind of question you're dealing with, what part of the titration. So 2.6, and I'm saying, right, I'm done with this point because there's a zero volume. Cool. All right. Now, I'm going to go after this point, which is going to be 0.4. What pH do we have here? I always think that this is the toughest problem, or one of the two toughest. I believe 0.4 and 0.3 are the two toughest questions. Okay? So, what do I have here? Well, if we think about this for a second, in a titration curve, as straight as I can do it, we're coming up. Whoa! Okay. We know something. We know our pH is going to be of greater than 7. Okay, because when I have a weak acid who barely goes forward, it's going to produce a conjugate base. Okay, and that conjugate base has an ability to react with the water. So this conjugate base, okay, will react with the water and grab. Remember, being a Bronston-Lowry base, you accept H pluses because it's got a lone pair. And you're going to make what? Hydroxides appear and reform the acid. The reason why it is a weak acid is because its conjugate base keeps reforming the acid. Okay? So party people, in the driven part of the reaction, I can't say this enough. Here it is. This is the driven part. Why that's small today is beyond me. Okay? And it's just above this point here. Now, this is the driven part. Okay? We're going to learn this is called the buffer region as well as I move into that tomorrow. But what am I after? I'm after this pH. What is this pH? Now, you should understand, at this point that we just found, there was 100% HA. And we're going to assume there's 0% what? A negative. At this point, we have driven the reaction completely forward. Okay? And so that we have what? 100% or 0% HA, which is the acid, and we have what? 100% of the conjugate base. So at this position, we have a theoretical position where I've driven the reaction so forward by adding what? A strong base, that all I have is that right there. So let's go back to, let's go write the driven reaction. The driven reaction is H. I just want to write it just so you know. It's the net ion. Well, it was C7, right? H5, right? O2, did I hit that right? Mm-hmm. Okay, cool. And I added the hydroxide. Now it's NaOH, but what do we know? That Na plus has no ability to ionize water. If it did, NaH would be sodium hydroxide would not be a strong base. So what's this going to do? This is going to yank an H away. We're going to drive it. No equilibrium here, party people. And guess what we get? You're going to get water, which we never measure because it's a liquid, but we get what? The conjugate base, which is negative. H5O2 negative. Party people, this is not equilibrium. This is driven. So if I use this to figure out something, I'm going to use moles. Okay? I mean, I could use molarity, but it's better to use moles. This is I would use Stoich table. So what did we find? I mean, other side. We found that we have 0.04 moles of H plus. Hey, they're equal. I don't know if I don't have to do this, but I'm just beating a brown pulp here. If these both are 0.0024 moles to begin with, and I'm writing moles so you remember, hey, this is stoichiometry. This is not equilibrium. This is a limiting reagent problem. Hey, this is 0.0024. They're both limiting. So this is 0 initially, right? I know it's silly. We're going to minus 0.0024. We're going to minus 0.0024. Hey, we're going to have 0 of this left. 0 of the base, because the base neutralized all the acid, forced the tan. But what are we going to have? Plus 0.0024. I know it's silly to write it, and you guys don't have to do this for this part of the problem. I'm helping you see it. Okay? 0.0024. Hey, I just made exactly the amount of acid that I started with. All of the acid was converted to that. So, what do I know to do this problem? I have 0.0024 moles of my conjugate base. For all intents and purposes, A negative to keep things moving. I want to know the what? The pH at this position, correct? So what do I need? Well, I need to know the concentration of the base. Okay? Why do I need the concentration of base? Because I have a new reaction, right? What's my reaction sitting in water? Hey, I've got this now sitting in water. C7, H5, O2, negative. If I don't have it there, now I do. That's impertinent. That's the big player here. It's going to sit in water because there's no acid to drive it. There's nothing. The base and the acid are gone. They've been neutralized. The only thing you have in water is H pluses and OH minuses that are naturally there. Okay? But this is going to be in equilibrium, and this base is going to ionize water. It's going to yank an H plus away. Bases are proton acceptors. So C7H5O2, it grabs its H back, reforms the acid, and of course produces the hydroxide. We need to measure that. Now, this is equilibrium. Sitting in water. I got a conjugate base that has an ability to react with water. This is equilibrium. To know your reactions is to know where you are in this, whether it's the lab or it's going in the opposite. So I want to solve for how much of this goes forward. I need an equilibrium table. Okay, you probably don't need an equilibrium table, but you need a concentration in molarity, not moles. So I know I have 0.004 moles of my conjugate base. The question is, party people, what's the volume? Well, at equivalence. At equivalence, I have 60. But what did I add to the beaker? What's in the beaker? 24. So at this position, I've added 60 milliliters of base to already 24 in the beaker. So I have 80 what? 84 milliliters of total volume. I've got to get that right. Understanding what you're doing is important. So this is 0.084 liters. And this will give me a concentration to do this equilibrium problem. And let's go do it. 0.0024 divide by 0.084. And I get, all intents and purposes, 0.029, we'll call it. Okay, and that's the molarity of my initial concentration before it starts dissociating. I am not going to do this. What do we know? The K is equal to x squared all over what? 0.029 minus x. X is gone for reasons ad nauseum at this point, correct? The only little trick here is if I use Ka, I'm not being aware of what I'm doing. The Ka measures how well this goes this way. We're going in the base way, so I need the Kb. All right? So what do I do here? Well, that's very simple. Ka times Kb equals Kw. So your Kb is equal to 10 to the negative 14 over my Ka, which was 6.3 times 10 to the negative 5, right? No? Okay. I'm amazed that I remembered that. Because these problems... Yeah?
What's the Kw stand for?
Oh, it's the equilibrium constant for water. Okay? I'm going to redo that derivation. So, 'cause I've been doing this, but you probably forgot why it works. So water barely dissociates. So think about the acid. So water breaks apart to H plus and OH minus naturally, but not much. Its equilibrium constant is 1 times 10 negative 14. It barely does that. Okay? So that's what Kw is. So I do second function e to the negative 14 divide by 6.3. Second function e to the negative 5. Okay, so I get my Kb to be, sorry to rhyme, 1.6, who cares, times 10 to the negative 10. Let's solve that. Times that, of course, by 0.029. Take the square root. My gosh, I feel like we've done this a million times. It's the same gosh darn thing. And I get my x to be, but careful, what are you solving for? My x is equal to a molarity. When I solve for x using an equilibrium, I'm solving for a molarity of something. So my molarity is 2.14 times 10 to the negative 6. That could be this. It's also this, and that's what I'm after. I'm after the pH. Hey, that's my hydroxide concentration. And how do I get pH? Well, let's go get POH. Negative log that, right? That sounds familiar. And I get a POH of 5.67. What do I do with that? Subtract from 14. Been through that a million times. And my pH, okay, after I negative log this, and then do 14 minus my POH, equals 8.3. That's my pH. at equivalence. That sounds a lot like what you just did for the lab yesterday, huh? You might have done it a little differently, but hey, you had to verify it. So 8.3, I know the volume, we just did that. So booyah, done there. Okay, I think 5 is an easy point. Let's go after that. Let's go after 5 now. 5 is the final pH. Let's go back to my graph here. Now, in my graph here, the titration is over at the equivalence point. Anything I add beyond this point is just extra, in this case, hydroxides. So what's the final pH? Hey, how many extra hydroxides do you have to the total solution? So what we do is figure out the total amount of extra stuff beyond the equivalence point. Since we ended at 90, right, this is 90, and this we said was what, 30, 60, thank you. I need help, definitely. There's 30 milliliters extra. Okay, let's go find moles of hydroxide. Why? I want concentration of hydroxide. Why? Because I get the POH from that. Booyah, I get that pH. So, how do I get moles? Well, I know the concentration of the base. I keep making it simple for myself. It's 0.1, isn't it? So I take 0.030 liters times my molarity. It's 0.1, right? Or is it 0.04? Ooh, you saved my 0.04, right? Darn it. I almost made a mistake. Thank you for almost stopping me. Okay. So 0.03 times 0.0. I could have done this in my mind. Okay, so 0.0012. What is that? What did I just solve for? Liters times molarity is moles. It's moles of what? Of hydroxides that were extra. But I want a molarity. So it's over 90, right? Over 30, right? Over the entire volume where the pH probe is in the beaker. We added 90, but there was 24 in it. 90 plus 24. 114. Point. Have to be in liters. This has to be a concentration. Molarity is moles per liter. So 0.0012 divide by 0.114. And I get a molarity that is equal to 0.0105. And what is that we just solved for? The concentration of my hydroxide in the final solution sitting in the beaker. I want a pH. Guess what? OH is a strong base. There's no equilibrium here. So as many hydroxides I have is how many I have. So negative log it. My gosh. This looks familiar. That does not give me a POH. It gives me, it does give me POH, not a pH. I subtract from 14. Sounds familiar. And I get a pH after I do a negative log and subtract from what? 14. I get a pH equal to approximately 12, 12.02. And let's put it on there. I know it's, oh. That was pretty aggressive. And I'm off, but who cares? Okay, I'm almost done. I want one more point. We're doing the point at what? What did I say? At 40. Okay, so we have the 40, but we don't know where the point is. So we want to know something here. And this is new. Okay? This is a buffer point. Okay, let me explain. When I added 40 milliliters of base, did I completely titrate this? But didn't I drive it forward somewhat? Hence the word driven. I'm adding strong base. I'm driving. Am I in equilibrium or stoichiometry part? Stoichiometry part. And therefore, I'm in this equation here. So what I'm going to do is I'm going to figure out how much acid is remaining, moles, how much conjugate base I made, moles. It was driven to a certain point. Remember, where are we here? We're like half equivalence is here. I'm asking you what this number is. We're still in this area. So I'm going to get rid of these numbers here. And I'm in the stoich table. Notice the arrow is not double. It is one way. Some people are bored already. Great. I love boring you because you got it. But I want everyone to be bored. So the first step is to know the moles of these guys. So let's do a Stoich table. Okay. Well, first of all, in the beaker, the moles of the acid is the moles of the acid. And we found that what? Doing the equivalence point way beyond we started here. So the moles of the acid, okay, is 0.0024. That's not changing. That's what we started with. 0.00 what? 24. I'm going to write mole to remind myself I'm in a Stoich table. I'm not doing equilibrium. This is driven. Now, question is, at, what was it, 40? 40 milliliters is 0.040, correct? Let's go find how many moles of hydroxide we are actually delivering. I've got the concentration, which is a molarity, which is that, and I'm timesing it by the concentration, which happens to be the same. Confuse myself. And what do I get here? 0.0016. What did I just solve for? Moles of what? Right, of the hydroxide that I delivered there. Mole, I'm writing it. Hey, this is a limiting reagent problem. There's no equilibrium. It's a 1-to-1. So guess who's the limiting reagent? Minus 0.0016. These guys are 0. We don't care about the liquid. Okay, water. And guess what this is? 0.00 Christmas. 16. This is going to go to 0 at the end, right? Because it's the limiting reagent. And how much acid is remaining? Okay, I think we can do that math. 0.008, right? 8. No. Yeah, I can do that. Maybe. Okay, now this is minus 0.06. What must this be? Plus 0.00. I know some people, Mr. Grodsky, I see it. Why are you bothering me? I'm sorry about it. Plus 0, it's 0.0016. So party people, we just came up with something really important. We have the moles of my conjugate base. We have the moles of my acid. Now we could do equilibrium, okay, but that means that I have to what? Go into a molarity. We could do all that, but why don't we just make our life easy and Henderson Hasselblock it away? Okay? And so, just to make some room here, I hate giving equations. What do we know? pH equals the pKa plus the log. This is given to you in your reference table. That's the what? Conjugate base over the conjugate acid. Now, we don't have a pKa. Excuse me, I believe that we do. Okay, pKa is what? 4.2. Now the question is, what are these concentrations? Now we could spend some extra time here, and I can do what? Take these moles and divide them by the total volume in the beaker. 40 plus 24, convert that and do all that and plug it in. But what do I know? Okay, I'm doing molarity over molarity. What's molarity? Moles over what? Liter over Christmas. I'm trying to make my point and I can't make it. Mole over liter is mole over what? Liter. Now if you haven't done this, what's going to cancel? The liters. So you can just put the moles right in. All right? So do that. Let's do that and solve for it. It's so gosh darn simple. This is a buffer equation. I'll talk more about it. So what is the log of A? Let's do the moles. A minus is what? So it's going to be the log plus the log of 0.0016. Let's get rid of the rest of this stuff here. Over what? The moles of this, 0.0008. What is 0.0016 over 0.008? 2. So let's do the log of 2 plus the what? 4.2. And what do we get? The log of 2. You get 2 logs. No. Log of 2, which is what? 0.3, right? Notice it's a what? Positive number. I'm adding it to 4.2. What's my pH? 4.5. And party people, we have finished our point. 4.5. Notice something. It's a little bit higher. This was 4.2, right? This is 4.5. Why is it a little bit higher? It's a little bit more what? Conjugate base. And then we what? We balloon up. Asymptote it. Approach the concentration of what? And you're done. Take a break.
Mr.
Please, someone stop that.
Stop what?